Thank you everyone, and welcome Dr. Bryan Ward. He is a neurotologist and a rising star in neurotology from Johns Hopkins. He is ENT surgeon by clinical profession, but he's also very much into engineering and biomedical engineering, particularly a very novel way of stimulating the neural tissues with magnet. Bryan will tell you about some historical aspects of it, but not too long ago, someone discovered that instead of electricity, which we used caloric test to stimulate your vestibular system, or not caloric, I mean galvanic test to stimulate the vestibular system, or heat or cold like caloric test to stimulate the vestibular system, we can also use magnet to stimulate the vestibular system. And it's kind of very amazing, and it picked up a new direction of research. And Bryan is at the forefront of that novel research direction. Big applications for that in rehab, in treatments, and many other things in future, hopefully. And perhaps Bryan might cover some of that in his talk too. Without any further delay, all yours.
Great. So let me share my screen. All right. Well, thank you so much. It's an honor to be invited to talk here. I want to thank Asif and Dr. Kirsch for the invitation. And I'm sorry I couldn't be there in person today. I swear it's not because I spent 5 years living in Pittsburgh. No hard feelings. I also want to thank Erica and Cheryl for all the behind-the-scenes work that they did for this talk. So the story I'm going to tell is how we came to understand the mechanism of how MRI machines cause vertigo. And I just think it's an interesting story in science, and hope you'll learn a little something about the vestibular system as well. So I have no financial disclosures. So the history of this goes back several decades. For over 30 years, people have been reporting temporary sensations of dizziness or motion around high-strength magnetic fields like MRI machines. This is increasingly happening around stronger MRI machines. So for reference, most of the scanners that we use today for clinical scans are about 1.5, maybe 3 Tesla scans. And increasingly, we're moving towards higher magnetic field strengths of 7 Tesla. So based on these sort of anecdotal reports, there's a group in Florida. There's this big basic science lab called the Mag Lab that has an affiliation with Florida State University. And Halped began putting rats and mice into these strong MRI machines, 14 Tesla, and then they observed that the rats and mice would circle after they left the scanner. And if they put them in water, you can sort of bring out this even more clearly. But interestingly, they found that if you performed a chemical labyrinthectomy on the mice, that is, that you gave them a chemical to destroy their inner ear balance function, they no longer had this circling behavior after exposure to the MRI machine. So our story began back in 2010. So this is David Z, who is one of my mentors. He's an eye movement neurologist at Hopkins. He lives part-time in Siena, Italy, or just outside Siena. And he was meeting with an otolaryngologist, Vincenzo Marcelli, there. And Marcelli had been doing an experiment where he was putting people into a MRI machine at 1.5 Tesla, and he was looking at functional MRI. So what that means is what parts of the area might be kind of having increased metabolic activity when a person is doing something in an MRI machine. And the intervention that they were doing was a caloric test. So what happens in a caloric test is you irrigate the ear canal with warm or cold water, and it causes vection in the semicircular canals and creates nystagmus and dizziness. And so he wanted to see, like, well, where in the brain are central projections for the vestibular system? And so he published his data in 2009, and in the discussion, he made this observation that there was a spontaneous nystagmus that happened even before the injection of water. So nystagmus is this kind of beating of the eyes, where the eyes drift slowly in one direction and beat the other way. And Marcelli speculated that this might be due to the magnetic field. And so he mentioned this to David Z, and Z brought this back to Baltimore. So in Baltimore, we had just installed this gigantic 7 Tesla MRI machine. These are really large. They required its own building. It had to be built on a special floating room to kind of shield it from the subway, which was just next door. And so he and Dale Roberts, who's an engineer at Hopkins, began putting healthy humans into the 7 Tesla MRI and observing their eyes. And the key is what you see here in this person, which is that they're lying in the MRI bore, but it looks like it's in darkness, and they're looking at the eyes with these infrared video goggles. And if you take care of patients who have vestibular disorders, you know that one of the kind of key hallmarks of a peripheral vestibular stimulus is that it can be suppressed by visual fixation. So if you're looking at something, you may not see any nystagmus. So you have to look at the eyes without visual fixation, which is what they're doing here. So here's a video of just, this is me, this is my eye, and I'm looking in darkness, but with an infrared video goggle. And I'm about to start going into the 7 Tesla MRI machine. And what you'll start to see is that my eyes are drifting in one direction and beating in the other. And this is that kind of characteristic nystagmus pattern. And you definitely feel like you're moving, at least I did. I felt like I was spinning for probably about 2 minutes in there. But what was interesting is that the nystagmus, this kind of beating of the eyes, lasted the entire time I was in the MRI machine. The perception is a strange one. The best way I can describe it is like this, where you're kind of lying on a child's, like a playground merry-go-round here, and your head is kind of moving in this direction and your feet are going in this direction, the axis kind of being about your navel. And it lasted about 90 seconds, and typically every single time I go in there I feel that sensation. So I have to review a little bit of just basic physiology of the vestibular system. So what I'm showing here is one of the semicircular canals, and we have to know a little bit about how we normally sense a head rotation. So if you rotate your head in this direction, what happens is you get a relative movement of endolymph in the opposite direction in one of these semicircular canals, and that displaces this thing here called the cupula. And that displacement of the cupula activates the hair cells that are embedded within it, and it sends this input to the brain that there's been an acceleration in that direction. So what happens is the fluid flow causes cupula movement, the hair cells bend, and you get a neural discharge. So these canals respond to an angular head acceleration, and the position of this cupula signals the velocity of the head. What's important to understand is that if you were rotating somebody at a constant velocity, like we sometimes do clinically, so if you spin them in a chair at a constant velocity, at first the cupula displaces and you get a nystagmus, but if you keep rotating at constant velocity, eventually this cupula will drift back to its original position and the nystagmus will eventually stop. To deliver a constant, you need a constant acceleration to get a nystagmus that persists on and on and on. So when we measure nystagmus, we take these videos of the eye and we threshold them so that the pupil is a big blob that's really dark in the image. And then if you track that position of pupil over time, you get these traces that look like this. So this is horizontal eye position versus time, and you get this sawtooth pattern, which is characteristic of a nystagmus. And there's 2 components to it. There's the slow phase here, which is the part that's due to the vestibular system. And then there's this quick phase, which is a rapid resetting. And if you take the slope of the slow phase, you get the velocity. How fast is the eye moving at over that epoch of time? And so what we do is we plot how fast the eye moves as a function of time. And you get traces that look like this. So before, I have to go over these traces because you'll see them several times throughout the talk, but before I do, I want to introduce you to just this line here. So this line is created with what's called a search coil, which is just a loop of wire. And so if you take this loop of wire and you basically put a magnet through the loop of wire, you're going to generate a current in the magnet. Or in the wire. But if you take the same wire and just kind of move it through the magnetic field, you'll also generate a current. And why that's important is that for these decades, people assumed that the cause of this dizziness was electromagnetic induction, because the perception is usually brief. It lasts for seconds. And typically when somebody experiences it, they have just moved into or out of the magnetic field. And so they thought it must be due to motion through the magnetic field. For our purposes, it's also a really useful marker for when someone enters and exits the magnetic field. So somebody goes into the magnet and they get this nystagmus that increases to a peak velocity. and then it starts to adapt, but incompletely. They continue to have nystagmus until they come out of the magnet, and then you get this reversal. So you feel like you're spinning in the opposite direction. Your nystagmus starts beating in the opposite direction, and the duration of this reversal is proportional to how much adaptation has gone inside the boar. So one of the first experiments was to kind of repeat what was already done in the rats and mice, which is take somebody who has no vestibular function in either ear and put them into the MRI machine and see if they have nystagmus, and they don't in any of the head positions that were tried. If you have no vestibular function on either side, similar to the rats and mice, you don't have this dizziness or nystagmus. So the key question then is, what could be the mechanism? And to figure that out, you got to think about all the different ways that magnetic fields can affect biological tissues, and there are several. So the first and probably the one that most people think of is magnetic susceptibility. So this would be something like your bar magnet on your refrigerator. So that would be ferromagnetism. And then there's weaker versions of that called diamagnetism, which is a weak repulsion, and paramagnetism, which is a weaker attraction. Electromagnetic induction is what I just introduced, where you move through a magnetic field and induce a current. And then there are these things, there's something called magnetohydrodynamics, which is the interaction of ion currents in fluids with magnetic fields. And this comes in two flavors. One is dynamic, and then one is static, which is called the Lorentz Force. So you need a strategy to kind of sort through these different mechanisms. Something dynamic obviously would require movement, and something static would not. And some of those mechanisms are sensitive to the polarity of the field, so and others are not. So for instance, your bar magnet is equally going to be attracted to the north or south pole of the magnetic field, so it's independent of the polarity. All right, so the first clue was that the MVS is static. So this is a 25-minute duration exposure to the 7 Tesla magnet. The person had nystagmus the entire time. The longest I've been in there personally has been an hour and a half, and I had nystagmus the whole hour and a half I was in there. So that nystagmus persists in the boar. The second clue is that it is proportional to the strength of the magnetic field. So it's roughly twice as strong in a 7 Tesla as a 3 Tesla. The third is that they allowed us to kind of put people into the magnet at different speeds. So we kind of decoupled the bed from the motor and just kind of pushed people in at faster rates. And you could induce a stronger electromagnetic induction, but there was no change in the nystagmus effect. So it's not related to subject velocity. And if you go in for a short duration, just about 40 seconds shown here, there's no after effect. So no reverse peak on exit for short duration. And the electromagnetic induction goes in both ways. But probably the most important clue was this one. So if you go in head first into the magnet, you have nystagmus that beats in one direction. If you go in feet first into the magnet, the nystagmus beats in the other direction. But if you go in head first into the back of the magnet, so the other pole, your nystagmus also reverses direction, which indicates that this mechanism is sensitive to the polarity of the magnetic field. And functionally what this means is that it rules out magnetic susceptibility. We have no iron in our inner ears, and we don't think it's diamagnetism that's kind of driving this force. So the data, this early data showed that it was static, it's continuous, it's not related to a transient induced voltage, and it can't be electromagnetic induction. And it's also sensitive to the polarity, so it reverses, the magnetic field vector reverses the nystagmus direction. Therefore, it can't be ferromagnetism or other magnetic susceptibility. All right, so what is it? So we think it's this, static magnetohydrodynamics. And you can think about it as if you have a charge and it's going through a magnetic field, you get a force on the charge. If you run those charges through a wire and you put that into a magnetic field, that wire is going to experience a force. And if you basically run that current through a liquid, then you're going to get a force in the liquid. So the equation for this thing called a Lorentz force is shown here, where the force, this Lorentz force, is proportional to the amount of current, the strength of the magnetic field, and then a scaling factor, which is the distance over which the current is flowing. So if you had, for instance, here a current in this direction, a magnetic field in this direction, then you're going to get this cross product, which is demonstrated by the direction by the right-hand rule, along the length of this column of fluid. shown here. And for our purposes, what's important is that the force is in the fluid. So here's an example of what this would look like in an experiment where you have a magnet underneath the table. You've got these two electrodes where a current is running across it. And this little bead is moving through a saltwater bath. And this is what essentially is Lorentz Force. This is static magnetohydrodynamics. So it turns out the inner ear is kind of a perfect place for all these things to happen. In your inner ear, especially in the vestibular system, there is current constantly entering the vestibular hair cells. These are the cells that kind of detect motion and vibration. And in order for the brain to figure out kind of where you are in space, there's always current active in both sides. And so if you turned your head to the right, for instance, you would have increased activity on this side and decreased activity on this side. And your brain does the math to figure out that you've just made a head rotation to the right. This current is supported by these potassium ions that are entering into the apical ends of hair cells. And when enough potassium ion enters, calcium enters the cell, which creates an action potential in the nerve. In the endolymph space here, the potassium is secreted by these things called dark cells. So potassium is constantly filling up the endolymph space, and with relative uniformity is entering in the apical ends of hair cells. What's shown here is the utricle, which is one of your gravity sensors. And then what's shown here is the cupula of one of the semicircular canals. So if you have this current constantly entering the apical ends of the hair cells and you introduce it into a magnetic field that's strong enough, you're going to get a cross product, you're going to get a Lorentz force that can, if strong enough, displace the cupula and give you a sense of rotation that you're spinning. So in this environment, the endolymph has two purposes of transmitting both current and force. So two key questions were still remaining, which is what is the source and the path by which you could get what's called a horizontal nystagmus? So that's the kind of eye movement we saw in that video. And then are the forces even sufficient to cause nystagmus? So for the horizontal nystagmus part, we just had to go to basic physiology of the inner ear. And one of the organs that generates a horizontal nystagmus is this one called the lateral semicircular canal. Another one that's in its path that can also potentially generate a horizontal nystagmus is the utricle. So the other part was basically a back of the envelope calculation just to figure out if the forces were even sufficient to kind of displace the cupula. So we did a calculation of how many hair cells were in the utricle and in each of the semicircular canal ampullas. We figured out kind of what the approximate resting discharge of each hair cell is. And then in a 7 Tesla magnet, you can do the math to figure out approximately how much pressure would be delivered to from the utricular current and from the ampullary currents. And fortunately, Oman and Young had already done the calculations to figure out how much pressure is required to generate nystagmus. And the forces, the amount of pressure was well within the range in a 7 Tesla MRI. So we felt that the forces were sufficient to generate nystagmus. So the forces are sufficient, but are the directions correct? And this is where you had to start manipulating the vectors. So you can, it's really difficult to manipulate the vector of the magnetic field. Basically, in an MRI machine, it's down the center of the bore and it doesn't change. But you can easily manipulate the head position by pitching the head forward, up or down. So this is one human who is going into the scanner at different head positions. And what you see is that they have nystagmus, and if they pitch their head forward, so chin to chest, you get relatively less nystagmus. And then there's this position here, which is called a null position. There's no nystagmus at all. And if that person can continue to pitch their chin to their chest, the nystagmus starts going in the opposite direction. And this was true for all of the healthy humans that we tested. So every subject has a null position, which is that they can go into the scanner and pitch their head to a certain position where there's no nystagmus. And if they pitch their head further beyond that null position, the nystagmus goes the opposite direction. But what's interesting is that the null position varies pretty dramatically by about 65 degrees across humans. So there may be different anatomic reasons for that, but it's still unclear. So the initial mechanism was this one, where the geometry was such that we thought the utricle current was the primary driver. And anytime you have a difference in the vector of the utricle current and the magnetic field, you're going to get a cross product. It's going to be maximal when they're 90 degrees to each other, and it's going to be 0 when they're aligned. And so if you figure out by the right-hand rule, you can stimulate this ear when there's this difference between the magnetic fields. But if you pitch your head down, the right-hand rule goes the other way, and you're going to reverse direction of your horizontal nystagmus. Another curious thing about this is that it's a useful tool to understand how the brain learns to adapt to a constant acceleration stimulus. So this is somebody going into the scanner, and you can see this kind of plateau that develops, that persists there the whole time. And when they exit the magnetic field, this adaptation creates this reversal phase where you're going in the opposite direction. And this is just a really interesting way of stimulating the vestibular system. It's the akin to a constant acceleration input, which is a really difficult thing to otherwise do. You can't rotate somebody via constant acceleration. And note, I think it's important to remember that there's a big dissociation between the nystagmus and the sense of rotation. So the nystagmus lasts the whole time you're in there. The sense of rotation usually adapts within about 1.5 minutes. The kinds of nystagmus patterns that we saw were pretty similar to what some of the classic vestibular physiology experiments showed. For instance, this one from Malcolm and Melville Jones in 1970 of a constant acceleration just for a short duration, which is essentially all they could do. And we similarly took the same subjects and accelerated them in a chair for as long as we could, and then showed that it was a similar pattern of partial adaptation followed by this after effect and adapting in the other direction. One of the common questions I got early and often when I give these talks is, well, we've been looking at the eye movements of people in MRI machines for decades. Why have we not seen this? And can't we just have somebody like look at a target to suppress the stimulus? So we investigated this by this design. So we had somebody outside the magnet in and out just like before. In one scenario, the person was lights off the entire time. And then we put them back in which we had the lights off in the beginning. We turned the lights on just after they entered the magnetic field and then off again right before they exited. And so what we saw is that outside the magnetic field, there's no nystagmus. And then if you go in, you get this increase to a peak. And then if you turn the lights off, you can suppress the nystagmus just as we'd expect. So it essentially goes down to 0. But what was really interesting is that if you turn the lights back on, off again, the nystagmus comes back to the same intensity as if the person had been in darkness the whole time. And then when they come out, the after effect, this reversal effect, is essentially superimposed. And why that's interesting is that it means that the brain is adapting to the stimulus even before vision takes effect. So, for vestibular rehab, we often, it's important that somebody receives error signals by moving their head. But to adapt to this constant asymmetry, the brain is doing it early, and it really doesn't care what vision is doing. It's just trying to stop feeling dizzy, regardless of what your vision you are. All right. So the first conclusion is that nystagmus in the MRI bore is explained by the effects of magnetic fields in the labyrinth, specifically Lorentz forces. And now that we had a mechanism, we wanted to begin exploring it more and trying to falsify it. So we began with humans with labyrinthine deficits, and then we had mice with different genetic mutations. We also used it as a research tool with zebrafish. So the first I'm going to talk about is humans with labyrinthine deficits. So this is an example of a person who has no vestibular system on one side. And you'll notice that we saw something that was atypical, that we hadn't seen in any of the healthy humans so far, which is that they developed, when they went into the magnet, a vertical nystagmus. So here the eyes are drifting down and beating up. So this is pretty atypical. We hadn't seen this in any of the healthy humans thus far. When I was in undergrad, I was a philosophy major, and I really love philosophy of science. This guy, Karl Popper, is someone who I have a great respect for. And Popper thought that nothing in science could be proven, it could only be corroborated, so you can build more evidence for your hypothesis. But one of the things that science can do is it can falsify. And so you can develop evidence that falsifies your hypothesis. So the question we had was, does vertical nystagmus, falsify this hypothesis of magnetohydrodynamics? So we wanted to parse out which parts of the labyrinth are affected based on the pattern of nystagmus, and we took 9 subjects. 5 had a left-sided loss and 4 had a right-sided loss. And the basic conclusion from the data was this, that most of the subjects had a horizontal nystagmus, just like healthy humans, but in addition to that horizontal component, they also had a vertical component, and the direction of that nystagmus sifted out depending on what side your loss was on. So if you had a right-sided loss, your eyes drifted up and beat down, and if you had a left-sided loss, the eyes drifted down and beat up. So to try to figure out what the heck was going on here, we just went back to basic anatomy. If any of you guys are interested, or if any of you are interested in inner ear anatomy, there's this really great free human temporal bone model that you can just download from this website here, and I'm happy to give you a link to it later. This is from the Massachusetts Eye and Ear Infirmary. So this is a right ear. This is the front, anterior, and posterior. And this thing here, that's the lateral semicircular canal. This is your cochlea. This is where the utricle is. This is the superior canal ampulla and the lateral canal ampulla. And what I'm going to do is take a look from the inside, and you can see that this is the utricular macula. So this is where we think this Lorentz force is kind of, the current is being generated. And here's the lateral canal and the superior canal. Krista? So if you swivel around from the back, and if you imagine that there was current entering the utricle here, as long as you introduce this into a strong enough magnetic field, you're going to get this Lorentz force. And you could imagine almost that if there was any endolymph flow in this direction, there might be also endolymph flow up towards the superior canal. So we kind of revised our hypothesis and introduced the superior canal in here as well. What we found is that in a left-sided loss subject, so if you didn't have this side, so just remember that this is happening in both sides on healthy controls. So if you didn't have this side, you would get a direction of flow in this orientation, which would stimulate this lateral semicircular canal, giving the horizontal component, and it would inhibit the superior canal. And for a right-sided loss, you would have the direction of flow that would also be similar to an excitation of this canal, but would be excitatory to the superior canal. So the nystagmus pattern you would get would give you nice horizontal nystagmus in the same direction, but verticals in the opposite direction. So in a healthy human, these vertical components would cancel, and that's why you wouldn't see any vertical nystagmus in a healthy human. One of the weird sort of idiosyncrasies about the eye movements would be that if you did the calculation to figure out the how the eyes ought to move, there should be a torsion, like a twisting of the eye. And so what we did is we developed a better video camera and a better way of analyzing the eye movements, and this is what we saw. So it looks mostly horizontal, but what is kind of interesting about it is that the eye is almost moving as if it's on a pendulum, which is a really strange pattern of nystagmus. So if somebody loses all function on one side, the eye usually kind of rolls like a wagon wheel, and that's the typical pattern we see clinically. This is a pattern of nystagmus we really don't see clinically, and maybe that accounts for some of the strange perception that you experience when you're in the MRI machine. So the results from unilateral loss patients and studies of 3D eye movements indicate that the superior and the lateral canal are stimulated, and we found by a similar amount. So next we wanted to see if mice had a similar kind of nystagmus response to humans. So this was an experiment in which 3D printed this sphere that would fit in a 4.7 Tesla MRI, and outfitted it with infrared LEDs, and then we put the mouse in the center of the magnet, because it had to be dark, just like in the humans. And the mice kind of get slid in like that. And here's an example of nystagmus in a mouse. This is going into a 4.7 Tesla MRI machine, and you can see that there's a pretty robust, primarily horizontal nystagmus. That's actually a lot faster than what we see in the humans, and in addition, it sort of tapers off and slows down really quickly. And that might be related to the mouse physiology for how it adapts to a vestibular stimulus. So we can quantify this by putting these little markers on the mouse's pupil after we anesthetize it, and we can get 3D eye movement recordings. And And when the mouse goes in head first, this is a position versus, or eye velocity versus time. And the nystagmus beats in one direction. And then if it goes in tail first, it beats in the opposite direction, just like the humans. So these were C57 black 6 mice. And we were looking for a mouse that had no utricle, but the best we could find was a mouse called a head tilt mouse. So these are mice that that don't have any otoconia, so they have no ability to detect gravity, but we assumed that they had normal vestibular ocular reflex because their canals were functional. So if you put them in water, they can't figure out where up is because they have no gravity sensors, and they have a head tilt. But what we found is that they did have a VOR. So this is basically a head impulse, a rapid acceleration, and in healthy C57 mice, the VOR, the head impulse is here, and in the NOx3 it's here. The gain of the VOR is a little decreased in the NOx3 compared to the C57s. We also did tilt experiments on them, and they had 0 eye tilt, as we'd expect, but all the C57s did. They did have responses to sinusoidal rotations, and pretty similar to the NOx3 mice, or to the C57s. But when we put them in the magnet in basically every position we tried, we couldn't generate any nystagmus in the 8 NOx3 mice. So what that essentially tells us is that the utricle is critical. So you need a functioning utricle in order to have this magnetic vestibular response, and that a canal ampulla current is insufficient. So the utricle is generating the current which induces a force that pushes on the neighboring semicircular canal, cupula. So mice do have magnetic vestibular stimulation, and those that don't have otoconia have no magnetic vestibular stimulation. One of my mentors, John Carey, came up with this interesting idea of using zebrafish, because zebrafish are this hot new model for high throughput screens, and they had been used for a lot of hearing screening for mutations, but we didn't really have a rapid vestibular screen. So I started putting zebrafish into magnetic fields to see what happened. And what I'm showing here this is an adult zebrafish in a cup outside an 11.7 Tesla magnet. And what you're going to see is what happens behaviorally when it goes into the magnetic field, that sort of flips and twists and turns and does so the whole time it's in the magnetic field. And sort of you can track this by looking at its position over time, and clearly it's much more disordered. Its swimming velocity increases when it's in the magnetic field. As a group in light and in darkness, the velocity of the swimming behavior increased. And in a second, you're going to see that as it comes out of the magnetic field, it's okay. I think it's okay. There was one time when I swore I saw nausea in a zebrafish. It looked kind of yellow and it was sort of panting, but they seem to be okay after that. This was another strange observation. So, we noticed that the zebrafish were diving towards the bottom of the cup, almost as if they were trying to dive into the direction of the magnetic field. So we took the same zebrafish and we put them into a horizontal magnetic field, just like a clinical scanner. And this is them outside the scanner, and what you're going to see is this strange behavior when they go inside, which is this. So they sort of dart in the direction of the magnetic field, at least in this fish. What was particularly strange about it is that you can take this fish out and put it back in, and it has the same behavior. It darts in the same orientation with respect to the magnetic field. But the fish had different preferences. So some preferred to dart north-south with a magnetic field. Some preferred east-west to the magnetic field, but it was a consistent behavior. So they seem to be able to sense this magnetic field orientation, at least, maybe not polarity, but at least a north-south, east-west somehow. So the profound behavioral disturbances that the zebrafish experienced happened independent of vision or lateral line function. I didn't show this, but we had them swim through gentamicin and then put them back into the magnetic field, and they still had the same flipping and turning behavior. Swimming in a bath of gentamicin destroys their lateral line, which is what they use to sense currents, but it doesn't get to the inner ear, at least when it's only a short duration exposure. And that kind of behavior is a similar behavior to what people have seen with fish that have hair cell deficits if they've removed their utricle, or if you've taken fish into outer space like they did on Skylab. They have that same kind of flipping and twisting behavior. So the forces stimulate the peripheral labyrinth, the lateral and the superior canals. It seems to depend on a functioning otolith organ. And we can use these tools to develop new research tools, but why should we care? So this is kind of where I put on more of my clinical hat. So I'm interested in inner ear imaging, and currently the state of the art is what I'm showing you here. So this is a high resolution CT scan of somebody's inner ear. This is using a flat panel CT scan, and this is the best resolution we can get. So this gives you amazing spatial resolution for bony anatomy, and we can use this to identify really tiny openings in the inner ear. But as you can see that the inner ear structures, which are, this is the vestibule where the utricle is, it's just gray, it's fluid density, and we can't really see much more than that. MRI, in theory, is supposed to be better for soft tissue. This is a 3 Tesla MRI of the inner ear. This is a heavily T2 weighted sequence so that it emphasizes fluid, and you can start to see some of the nerves in contrast to the fluid around them. But the inner ear is filled with these like artifacts, and you can't really tell, is that a normal structure or not? One of the cool things that has excited people in my field about inner ear imaging is that you can give gadolinium, and the gadolinium gets into part of the inner ear if you wait long enough, but not the other part. And so you can start to see contrast between the perilymphatic space and the endolymphatic space. And this might be useful in disorders like something called Meniere's disease, where people develop a swelling of their inner ear, and it causes them to have recurrent vertigo episodes. But the resolution just isn't that great. One of the basic principles of MRI is physics, really, is that the more magnetic field strength you have, the more signal that you have available to use. So Siemens approved a 7 Tesla MRI for brain and knee in 2018, and GE had approval last year for their 7 Tesla scan. Philips is still pending. But as you know from earlier in the talk, higher magnetic field strength is directly proportional to the amount of Lorentz force and the amount of vertigo that people experience too. So recall that in a 7 Tesla, the nystagmus and dizziness is roughly twice that of a 3 Tesla. So here's a patient that we had on our service. This is somebody who had this pituitary tumor removed. And we often get these high intensity magnetic field scans within the first couple days after their surgery as a baseline scan. So this person got a 3 Tesla MRI scan, and just as they were coming out of the magnetic field, they vomited because they felt dizzy. And then they developed that increased in intracranial pressure caused them to get a CSF spinal fluid leak. And they had to spend an extra week in the hospital for that. So I heard this at one of our morbidity and mortality conferences, and was able to get that patient to come back and go into that same exact scanner 6 months later for their post-op scan. And I put some goggles on her. And what I saw is that she had a little bit of a nystagmus when she went into the scanner, but she had this big reversal where she reported she felt like she was moving as she was coming out of the magnet, but this time she didn't vomit. So there are potential safety concerns in vulnerable patients going into these really strong scanners. Another reason to care is functional MRI. So resting state studies in which people are presumably not doing anything require somebody to basically sit in a scanner for a long period of time, and they look for synchronized firing of different parts of the brain, synchronous bold signal. And one of the things they didn't account for is that you might be getting constant vestibular stimulation the entire time you're in the magnetic field. So Rainer Bögl in Germany, in Munich, was looking at patients in 3 Tesla and 1.5 Tesla functional MRI. And he made this good observation, which is that the amount of signal, the bold signal, increases non-linearly with magnetic field strength, but the amount of Lorentz force increases linearly with magnetic field strength. So if you kind of put your seeds in different parts of the brain and you look at the parts that you think are related to the vestibular system and those that are not related to the vestibular system, you should see differences between the increase in activity. And what they found is that all the parts that are associated with vestibular function increase linearly with magnetic field strength. And in the non-vestibular parts, it increased with the non-linear increase that you would expect for the stronger magnetic field. So it was kind of proof, or somewhat of a proof, a support, I would say, that that this might be a contaminant of some of these resting state studies. The final and kind of cool, just sciencey reason to care about this is magnetoreception. So we still don't really know how animals detect magnetic fields to migrate. We know that they do, but there is a really high stakes debate that's going on in the literature to try to figure this out. So there was a paper in Science that thought that there were magnetic particles in the beaks of homing pigeons. There was another paper that came out about a decade later saying that that was an artifact. There's a big group of people who think that magnetic field can be seen by birds based on these magnetic particles called cryptochrome in the retina. And then there was this study by Wu and Dickman where they did single unit recordings from the vestibular nucleus of homing pigeons. And they rotated a magnetic field around the pigeon, and they found that there were cells within the vestibular nucleus that could encode both the direction and the intensity of the magnetic field. So at the very least, there's information being processed through the vestibular nucleus on magnetic field sensation. It's still unclear whether the periphery, though, is the source that's kind of sensing that. So the take-home messages are that MRI magnetic fields stimulate peripheral vestibular system by the static Lorentz force. The lateral and superior canals are stimulated, and a functioning utricle is necessary. And magnetic vestibular stimulation could be a useful research tool for zebrafish as high-throughput screens, or to understand how we learn to adapt to a constant new set point. It's going to become more prevalent with stronger MRI, and we need ways of kind of addressing that. So I want to give a thanks to the funding agencies that support me, and most importantly, my mentors. So Dale Roberts, Charlie Delacentina, John Carey, and David Z at Johns Hopkins, and then also my collaborators who are now spreading throughout the world, but Michael Schubert is still at Hopkins. So thank you so much for your time and attention, and I'd be happy to answer any questions.
Dennis has a question, and Alam has a question. Dominique has a question. Dominique?
Yes, thank you very much. Very interesting talk. So one question is about the actual nature of the effect. So you started with a current. There's a current that is continuously going, right? And when there is a magnetic field applied, then there's a force there. So that's very similar to a blood Doppler measurement system where you have ions in the blood passing through a magnetic field, creating an electric field along the sides of the vessel, and that field can be detected. So my question is, first, is that current similar to the dark current that you see in retina, in the cones, for example, where you have this continuous current going on? Is that correct?
I think so. I don't know enough about the magnitude of the dark current in the retina, but I would expect that there would be a Lorentz force also happening in the retina, and it's interesting because I've had this hypothesis that in some of the magnetic field, the MRI sequences, you can see these things called banding artifacts that happen in different parts of the fluid signal. So they're common in the retina, they're common in the inner ear, and I sometimes wonder if those might be sort of distortions of the magnetic field related to the current going through these structures.
In the retina, though, there are excitation, but these are due to the gradients of an MR, not to the actual DC field. But now I'm thinking maybe it's something else is going on.
Yeah.
Did anybody report like perceptive visual signal, like kind of flash in scanner?
Yeah, so that's pretty common actually. In 7 Tesla and strong MRI machines, and I experienced this, is that if you make a saccade through the magnetic field, you get these phosphines. So phosphines, for me, what that experience is like is that every time I have a quick phase, I see a distant phosphine that looks like heat lightning almost. That's kind of how I describe it. And it occurs with every quick phase.
We do see phosphine commonly with DBS. When we turn on the lowest lead of GPI contact, near the optic nerve. So it is pretty strong then. I mean, this is as strong as DBS. Interesting. So, but only when you make a saccade. So it is more like when you create a retinal, not really a retinal slip, but why with saccade?
I think the thought is that there's an induced voltage, like an induced current from the movement of the retina through the field.
But there's also phosphine produced by the gradients. When the gradients, the MR machine turn on and off, you can induce phosphines directly.
Cool. Yeah, we did scan. We've done scans as well, and it doesn't seem like it modifies the nystagmus pattern, but I assume that the gradients probably have some small effect.
Alan?
Yeah, hi. Thank you. It was a nice talk. I have a question about this function. So the vestibular hair cells, the way that they oriented is a little bit different than the cochlear hair cells. So the cochlear hair cells have this nice kind of shape and all of them facing the same direction. But when you look at the vestibular hair cells, they are actually facing the opposite direction. So that's one of the reasons why we kind of know where we are if we move our head. So my question to you is, like, when you have the patient, you ask them to tilt their head a little bit in a different direction. Do you think that has to do with the orientation of the hair cells? Because it seems to me it seems like this is more like a mechanoreceptor kind of response, like where these channels like open. It has to do with like where you are in the position of the hair. So does the hair cell orientation has something to do with that?
Yes. So the hair cell orientation matters a lot. So when we think of the utricle is kind of mostly a planar structure, and it has the highest hair cell count of the labyrinth. So that's about 30,000 hair cells. And so that should be relatively similar between the two ears. And if you have a current that's going into both ears and you align that up with a magnetic field, then you would get no cross product. It doesn't seem that the cupula current, or the ampullary currents are enough to generate this response. And it is a mechanical response. So the utricle is generating the current, but there's a force that then pushes on the cupula and causes the nystagmus to occur. In the mice, I didn't show this, but you can, there are null positions where you can line up the utricular current with a magnetic field. We assume it's the utricular current, and you get no nystagmus. And then there's also positions where you can turn the mouse like 90 degrees orthogonal to the magnetic field, so that the Lorentz force should be the same, but the direction of the force is just not directed towards the cupula, and it doesn't cause nystagmus either. So you have to have, so there's both a mechanical part to it as well as a current part that has to line up with the magnetic field. Does that help at all?
A little bit. I'm still like, I have to imagine the orientation, because when you also put the zebrafish into the whole story, now the zebrafish has this lateral line, which is a hair cell also. So, and they were tilting, and this kind of like showed like they are not balanced themselves. So it's kind of.
So yeah, to clarify a couple things that I didn't go into in greater detail. The mechanism, I think, for the mice is probably similar to what's happening in the humans. The zebrafish, we did destroy their lateral line, and they did have the same kind of flipping and turning behavior. So it's independent of the lateral line, but a big caveat there is that the inner ear of a zebrafish is very different from the inner ear of a mammal. And so they have these large calcium carbonate crystals called otoliths rather than sheets of otoconia. And when you have a mass of that size, you actually can get some really strong diamagnetic forces potentially on that mass. So if the fish is swimming through the magnetic field, there may be something else going on where it's twisting or turning that utricle and causing this completely disorienting behavior for the zebrafish. So in theory, you could record nystagmus in a zebrafish as well. We found that very difficult to do, and so didn't explore that anymore. But I think it's related to the inner ear, but it could be a different mechanism. And you have to kind of basically go back to the first principles of like going through electromagnetic induction and all those things. Yeah.
Dominic?
Yeah, it's just a clarification still on the end product here. So in the Doppler measurement system, there is a force, but the force doesn't do anything except pushing the ions on the side, which produce an electric field that can be measured. In the case of the vestibular system, is it the force producing a nystagmus, or is the force pushing ions producing an electric field, which then activates axons?
Yeah, it's a good question. We think we hypothesize that the force is causing a flow of fluid within the vestibule, and that flow, that constant flow, is pushing on the sensors, the shear sensors of the cupula, and causing that. One of the things that I'm trying to do now is actually image flow in the vestibule. So there are special kinds of contrast imaging called phase contrast imaging, where you can image flow, usually of blood vessels at really fast rates. And so, first we have to demonstrate proof of principle that we can even image at this incredibly low flow rate. We're thinking about a millimeter per second. So it's, but if we could demonstrate that, that would be helpful. But you're right. I mean, I can't, at least off my top of my head, rule out that there could be a secondary magnetic field or electrical current that's kind of stimulating the cupula.
But even in your case with the force, that force only applies to charged particles. So I'm assuming that the solution that's moving with the force is composed of ions.
It is, yeah. It's a potassium rich, yeah.
Potassium ion, yeah, okay.
I had a very interesting observation, and this was around the time when I used to take overnight call and not sleep and sleep in the hospital. This was around the time when Dave Z described in the current biology paper, 2011. So stroke patient rolls in, cerebellar infarct, constant nystagmus, throwing up, vertigo. And then, like when acute phase, when stroke patient comes in at main campus, we directly take them to the scanner in the ER. And I take him to the scanner in ER, comes out of the scanner, no nystagmus. So I wonder whether, these are 1.5 Tesla scanners. These are not that powerful scanner, but nystagmus was really robust. And there was a massive nodulous infarct. So I know that there was a lesion. I know that there was a nystagmus which correlates with that. I know that he went in the scanner and it disappeared. So can you reset the central rhythm generator with a strong, it's almost giving a zap in the periphery to reset the central rhythm generator, right? So have you noticed anything like that?
No, we haven't, but it's a great observation. It reminds me of like periodic alternating nystagmus and delivering
almost, yeah.
Right time. So maybe, yeah, possibly. I think one of the interesting things that have come out recently is that a separate group found that there's being in the scanner induces like almost like a neglect. Like you start to favor one side of your people have done caloric studies for people with hemi-neglect, and you wonder if maybe this could be a useful treatment for that too.
So yeah, caloric and hemi-neglect, it's like it's a right hemispheric predominance, right? And yeah, I know that stuff, yeah. FWM has a question.
Yeah, hi, this is Fred.
Oh, Fred.
Interesting talk. When you did the left versus right with the damage on left, and you got the vertical nystagmus, because of I haven't quite figured out all the coordinate transformations yet, but did you get a vertical or at least up nystagmus versus down nystagmus in the left versus right because of the mirror image?
Yeah, that's exactly right. Yep. Yeah, so there was a difference between the two sides where a left-sided loss had a slow phase down up beating and a right-sided loss had a slow phase up down beating. In addition to the horizontal component that was still there.
Yeah, thank you.
Great.
Well, if nobody asking, I'm asking one more. So on the last part of your talk, you talked about animals that can maybe detect magnetic fields, and clearly this is a really interesting topic as well. Clearly, that cannot be the same mechanism that you're talking about, because it's operating under extremely smaller magnetic fields of the Earth, or 50 microtesla, which is nothing compared to the 7 Tesla you guys are talking about. If you were to put these animals in an MRI 7 Tesla machine, something serious might happen. Clearly, there's something going on in these brains that is extremely sensitive to magnetic field. And wouldn't that cause damage if you were to do that?
Maybe, if we can figure out where the sensor even is. But yeah, it's an incredibly strong magnetic field, and you wonder if it might be able to, it might damage the sensor. I mean, I was a little worried about that in the mice. I mean, people with mice, they think that they might be able to detect some magnetic fields, and the velocity of the nystagmus that we had, it almost seemed like we were overwhelming their ribbon synapses with the stimulus. Interestingly, the way that the force scales, the smaller the diameter of your semicircular canal, the stronger the effect will be with the same magnetic field strength. So it's kind of a way of increasing the gain, but you're right, it's orders of magnitude higher than ambient magnetic field of the Earth. So it could be an entirely different mechanism too.
But mice don't walk in the direction of the magnetic field, right? They don't.
They don't.
Like the fish do.
No, I know, and you know, there's all kinds of studies of that talk about things like, you know, that they can build nests in the southeast corridor or something like that, and you change the magnetic field strength. You know, there's some subtle behavioral things, but the evidence isn't quite as strong as it is in like homing pigeons and sea turtles.
So what's your opinion then on the homing pigeons detection mechanism?
They did find these kind of iron balls in the hair cells of some homing pigeons and other animals that do seem to be navigating with magnetic fields. And I wonder if that has some way of kind of increasing the gain of the signal. I'm not entirely sure, but it's I don't think there's been a clear hypothesis. We have some hypotheses, but I don't think I'm going to be able to do single unit recordings in pigeons soon.
Okay. All right. Very interesting. Thank you very much.
Thanks for the great discussion.
Thank you.
All right.
Thank you very much, Brian. A real pleasure to have you here today. I feel a little lost here. I'm supposed to be making an announcement about